In this video, we're going to learn how to use Kruskal's algorithm to find the minimum spanning tree. So take 3 deep breaths and let's make this math easy. All right, so just as a reminder, a tree is a connected graph that does not contain any circuits. And a spanning tree is a subgraph, which means like you're just taking like parts of the original graph. And that subgraph needs to be a tree and contain all of the vertices of the original graph in order to be a spanning tree. So Kruskal's algorithm allows us to find the cheapest spanning tree in any given graph. So the way that Kruskal's algorithm works is you basically choose the cheapest or shortest unused edge in the graph, and you just do that over and over as long as choosing the edge will not create a circuit. Because the goal is to create a spanning tree, and if you create a circuit in your subgraph, then it won't be a tree. And so you just continue doing that until all of the vertices are connected, and then that means that you're done. So as an example, let's say we wanted to find the minimum spanning tree in this graph. Well, I would basically just look at it and say, okay, well, what's the cheapest edge? It looks like it's this one right here. So I would use that edge in my spanning tree. And then it looks like my next cheapest edge is this $5 one. And the next cheapest one is the $6. But if I use that $6 edge, that would create a cycle, which would mean that it wouldn't be a tree. So I'm not going to use that edge. The next cheapest one, it looks like, is this $7 one. And then the next cheapest one is the $8 one. And now at this point, all of my vertices are connected to each other because I can get to any vertex from any of the other ones. And so I'm done with Kruskal's algorithm. And the cost of this minimum spanning tree is going to be 4 plus 5 plus 7 plus 8. And that would add up to 24. And so the cost of this minimum spanning tree would be $24. And this can be applied in real life whenever you have like a network type of situation. So for example, maybe like if all of the vertices represented power plants and you wanted to build power lines, like high volume power lines that can handle a lot of electricity between the power plants. Maybe the edges represent how much it would cost to build those power lines. I mean, probably it would be like in millions of dollars, you know, not just $4, but you could find like the cheapest way to connect all of the power plants by finding the minimum spanning tree. But it also doesn't have to be a complete graph. So in this example, it was a complete graph that we found the minimum spanning tree. But you can also have one where all of the vertices are not necessarily adjacent to all of the other ones. So if you wanted to find the minimum spanning tree for this graph, it looks like the cheapest edge is 1. And then the next one, we actually have multiple edges that are 2. But if I add all of these to my subgraph, it won't create any cycles. So I can use all 3 of those edges that are a cost of 2. And then 4 is the next cheapest. So I could use this edge and this edge. But if I use that edge that's a 6, it would create a circuit right here. And so I'm not going to use that edge because I want the end result to be a tree, which means that I can't have any circuits in it. And then the next cheapest edge after that is the 7, and that doesn't create any circuits, so that's good. And then the next cheapest edge is an 8. And we actually have 2 8s here, and it doesn't matter which one we use, but we can't use both of them because if we were to use both of them, then we would have a circuit that went through there. And so I will only use one of them. And I'll just choose this top one, but you could have chosen the other one and that would be fine as well. And at this point, all of the vertices are connected to each other. And so that means that I've got a spanning tree because I've connected all of the vertices together. And the cost of this minimum spanning tree would be 1 plus 2 plus 2 plus 2 plus 4 plus 4 plus 7 plus 8. And that would equal 30. And so the cost of this minimum spanning tree would be 30. And it still would be 30 even if you had chosen to use this other 8. Your spanning tree would just look a little bit different. So it would be a different spanning tree, but they would both cost the same. And so they are both considered minimum spanning trees. And you can also do this if you have a graph that's represented as a table instead of with a graph diagram. And so let's say that we had, it looks like this is a complete graph because every vertex is adjacent to all of the other vertices. If I wanted to find the minimum spanning tree, the main thing I need to look out for is not creating circuits. And that's really hard to tell if you have a circuit in a table. So it's often helpful to draw out all of your vertices and like connect them as you choose your cheapest edges to make sure that you don't have any circuits because it's kind of hard to see circuits in a table. So I'm going to make a point for Ashland and Astoria and Bend and Corvallis. I think I'll just have a C for Corvallis and then a CL for Crater Lake, and then E for Eugene, N for Newport, P for Portland, SA for Salem, and SEA for Seaside. Okay, so these are all of my vertices, and I'm going to look through my table to find the cheapest edge. So it looks like the cheapest edge is this 17, and this is the same 17 that is represented here because remember, in tables, the weights of the edges are always listed twice because this is saying like, oh, Astoria is adjacent to Seaside, but Seaside is also adjacent to Astoria. So essentially it like counts for both of those. And so you actually don't really have to pay attention to the bottom half of the table because those are all just duplicates of the top half. So I would say, okay, 17 is my cheapest edge. So I want to include that edge. So Astoria to Seaside, I'm going to connect those two because I'm going to use that cheapest edge. Then I look for the next cheapest edge and it looks like 40, I think, is the cheapest one after that. And so I would say, okay, well, the 40 edge is between Corvallis and Salem. So I'll connect those two. And then the next cheapest one, I think, is 47. And there's actually two of them. So I'm going to look and see if it would create a circuit. So Salem and Portland, that would be that 47. And then Eugene and Corvallis, it looks like it doesn't create a circuit. So we're good if we use both of those. And then the next cheapest edge is 52, I think. And so that connects Newport and Corvallis. So that would look like that. And then the next cheapest one is, I think it's the 64. And so 64 connects Salem and Eugene. But if I were to connect Salem and Eugene, that would create a circuit. So I'm actually not going to use that one. And I'm going to cross off the 64 because I don't want to use that one. Then I would look for my next cheapest edge, and it looks like it would be, I think, the 78, which connects Seaside and Portland. So these two would be connected. And then 84 is Portland and Corvallis. But if I do Portland and Corvallis, that creates a circuit. So I'm not going to use the 84. Oh, and I actually skipped this one. 83 was cheaper than 84. But Newport to Salem will also create a circuit, so I'm not going to use that one either. And so the next cheapest edge after that is 91, which is Eugene to Newport, which would create a circuit, so I'm not going to use that one. And the next cheapest one is 95, which is Astoria to Portland, which would also create a circuit. So later on in the algorithm, you're going to have a lot of edges you won't be able to use just because they create circuits. So the next cheapest one after this, I think, is 110, which is Eugene to Portland, which creates a circuit, so we won't use it. And then I think we have 114 is the next cheapest. So Newport to Portland, again, creates a circuit, so we're not going to use that one. I think 117 might be the next one, to be Newport to Seaside, which again creates a circuit. And so basically you just keep on doing this. Oh, and I actually missed this one. 108 was much smaller. So 108 connects Crater Lake to Ashland, connects those two. So we will end up using that one. And then I would have 118 Salem to Seaside, but that creates a circuit, so I won't use that. 128, there's two 128s, and so that would be Bend to Corvallis, which works there, and Eugene to Bend, but like I can only use one of them, I can't use both of them, because if I connected Eugene to Bend after I already connected Bend to Corvallis, then I would create a circuit. So I'll only use one of them and then I'll cross off the other one. And let's see, what's the next cheapest one? I think actually, so at this point, we have kind of like two parts of the graph that are not connected yet, because we have this part right here where all of these vertices are all connected, but we have the Ashland to Crater Lake part that's not connected. So I think the best way to do this would be to just look at Ashland and see which ones are cheapest and which ones are cheapest with Crater Lake, and just get it connected in some way. So if we look at Ashland's row, we can look at it and say 178, it looks like, is the cheapest in that row. And connecting Crater Lake to the graph, there's nothing that's cheaper than that. Like if we look at the options that are connecting Crater Lake. And so I think the 178 is going to be that last edge that we need to connect Ashland to Eugene. But if you kept on repeating the cheapest edge over and over, you would eventually get to that. But sometimes at the end, like if you only have like one last little piece you need to connect, you can just kind of shortcut the algorithm a little bit. But that's how you would do it if it's a table. So you still look for the cheapest edge and keep adding the cheapest edge until the entire graph is connected. You just have to make sure that you don't create any circuits within your graph. So that's how you use Kruskal's algorithm. If you have any questions, let me know.